All right. So I'm not going to use my computer for this talk. I'll use the board. So I want to talk about computing moment sequences of Sato-Tate groups. So this talk has nothing in particular to do with number theory, per se. This is really just about theory of compact Lie groups and probability theory, but moment sequences are an extremely valuable tool for analyzing Sato-Tate groups, and in particular for analyzing the Sato-Tate statistics associated to a particular abelian variety. So I want to explain how we go about computing them. Okay, so start in slightly more generality. So let G be a topological group. And let's assume that it's compact Hausdorff. All the groups we're interested in are. Actually, for the first part of what I'm going to say, being locally compact would be sufficient, but it's simpler to state things if we just assume we're in a compact group. And I'll just recall that a Borel set in G is an element of the sigma algebra generated by the open sets. And by sigma algebra, I just mean what you get when you take complements and countable unions and intersections. All right, and then I guess a key fact is that if we take any element of our topological group and any, so I'm going to give the sigma algebra a name, call it capital sigma, and any set, any Borel set, if I take the translation of S by G, i.e. multiply every element, I get another Borel set. Okay, and then we say that a measure on sigma is translation invariant. And I'm just going to write things on the left, but we could define it equivalently if we wrote it on the right. If the measure of GS is the same as the measure of S for every element of our group and every set S in our sigma algebra. And then the main theorem that I think has been used in just about every talk, but I thought it worth stating it for this one. This is Haar's theorem, although it was actually proven sort of in full generality by Weyl. There exists a unique translation invariant measure on our topological group G, compact Hausdorff, with the following properties. To make it unique, we want to normalize it, and since we're going to use it as a probability measure, we may as well normalize it so the probability of the whole group is 1. The second requirement is that we want it to be what's known as outer regular, which means that for every Borel set, if we take the measure of the set, this is the infimum of the measure of all the open sets containing S. And then the third requirement, known as inner regularity, says that for any open set U, the measure of U is the supremum of the measure of S for any overall the closed subsets. And really I should say compact here if I was going to define it more generally, but since we're in a compact Hausdorff space, these are the same thing. Okay, so this is the Haar measure that we're going to use, that we now want to consider for particular topological group, compact Hausdorff topological group G. So you can do this for any of the classical compact Lie groups, but we're going to focus on USP 2G, since we saw that that's where, for abelian varieties, anyway, that's where their Sato-Tate groups live. And so so we know that if we take a matrix in USP 2G, its eigenvalues come in conjugate pairs and they lie in the unit circle. That is sort of a basic property of being both unitary and symplectic. So let's write down the eigenvalues. So these are all sitting on the unit circle. And there's 2G of them, but they come in conjugate pairs, so I'll just consider G eigenvalue angles, and I'll may as well insist that they're in the upper half plane. I'm sorry. Okay. All right, so with this notation, the joint density function of the eigenangles, so think of it as a tuple of eigenangles, given by the Haar measure, so this is due to Weyl. So mu of USP 2G. So it's 1 over G factorial. Then we take the product over distinct eigenangles of 2 cosine theta j minus 2 cosine theta k squared. And then we take product over the eigenangles of sine squared theta j, d theta j. Okay, so for any G, we can use this to explicitly compute the joint density function for these eigenangles, and this will let us compute probability measures on the trace or on any of the coefficients of the L polynomials. The random variables that we're interested in are precisely the symmetric polynomials in the eigenangles. Those are the coefficients of the characteristic polynomial. And so, for example, if we wanted to compute the trace, or the, say, the A1 coefficient, which would be minus the trace, this would be minus the sum of 2 cosine theta I, where I runs from 1 to G. And similarly, we could write down A2, A3, etc. So this is the joint density function implied by the Haar measure. Strictly speaking, here I'm taking the image of the Haar measure on conjugacy classes when I write down this joint density function for the eigenangles, but that's more convenient. I mean, if I was going to write down the Haar measure, I'd really need I would integrate over conjugacy classes and then integrate within conjugacy classes as well. Okay, but this is sometimes known as the Weyl integration formula. But since we're only interested in elements of the Sato-Tate group up to conjugacy, this is the measure that we want to work with. So let's look at a particular example. So let's just take G equal 1, check that this gives us the Sato-Tate measure. So take mu of SP2, and recall that USP2 is the same thing as SU2. If you're going to preserve a symplectic form in your 2 by 2, you have to have determinant 1. Yeah, fine. Yeah, this notation is common. I mean, this is used in Katz-Sarnak, and yeah. I don't mean the measure of the whole group. Yeah, I understand what you're saying. Now I understand why I'm confused. Yeah, so I could be better to write this as mu of theta 1, theta k. Okay. So yeah, I'll put it with subscripts. Yes, I have an inconsistency between the left and right-hand sides of the board. So mu SU2. So this is going to be just, well, 1 over g factorial is 1. This term is going to be 1 because there's only one eigenangle, so I don't get any terms here, and I'm just going to have one of these. So I'm going to get 2 over pi sine squared theta d theta. So this is the Sato-Tate measure that we've already seen. We could also write this in terms of the trace, or in terms of the A1 coefficient equivalently. If I just make a substitution, replace, let me write down first. And here t is 2 cosine theta. Okay. And so here you can see the semicircular distribution going from -2 to 2. Okay. All right, now let's look at genus 2, which is what I'm going to focus on in this talk. So now we want mu of USP4. So if you plug in to this formula, you're going to get 8 over pi squared cosine theta 1 minus cosine theta 2 squared sine squared theta 1 sine squared theta 2 d theta 1 d theta 2. And it's a little more informative to again do a change of variables. So I'm going to write change from theta 1 theta 2 to a1 a2 because that's in our experiments, that's what we're actually measuring. So I can get the joint density function for a1 a2, and it takes a little bit of calculus to work this out, but the end result is we get a nice okay, so I have the square root of a quadratic here and 2 linear factors. And I need to say where the support is. I mean, for here, this theta, so this is theta 1, theta 2 are between 0 and pi. Here, our region of support is we're going to require that a2 is greater than or equal to both plus and minus 2a1 minus 2. And then it's bounded above by this parabola. And this is just saying that all 3 of these factors under the square root are positive. And if you draw this, so these 2 lines are going to make a V, and the parabola here is going to look like this. So this is the point 0, minus 2, if I'm thinking of the A1 axis as horizontal, the A2 axis is vertical. And this would be the point minus 4, 6, 4, 6, and then this point right in here would be 0, 2. Okay, so this parabola is exactly the parabola that goes through these points, and these are the 2 lines. And so the support is inside this region. And if you recall, when I showed the joint distribution, when I compared the moment statistics for a generic genus 2 curve with the values you get when you integrate the Haar measure over this region, when I rotated the island so that we were looking at the A1, A2 axis, we saw exactly this picture. Okay. All right. And once we know the joint density function of A1 and A2, of course, we could then integrate over A1 or A2 in this region of support to get the probability density function for either A1 and A2. But of course, they're not independent. So we would need to, we are really, in general, interested in their joint density. All right, so I'll move over here. Actually, maybe I'll go to the center board now. Yes, the image of the Haar measure on conjugacy classes, yes. So now I want to talk about moments. So again, I'll state things in a little bit of generality first before we specialize to the case of interest. So let's x be a real random variable. And just recall the nth moment of x, which I'll denote m sub n, and square brackets around x. This is just the expectation of x to the n. And if I drop the n, I'll just be denoting the moment sequence is just a sequence of moments. In our case, they're going to be integer sequences, but in general, they could be sequences of real numbers. And I'm always going to start the sequence at 0. We'll see why, which might seem kind of silly because the 0th moment is always 1, but it's actually quite convenient to always have that 1 sitting there for computations. Now, the first question you might ask is, do these expectations, do these moments necessarily exist? And in general, they might not. The random variable x might have an expectation, or even if x does, maybe x squared doesn't. So just as a note, we will note that provided if x has bounded support, then all of its moments exist. That's going to be true for any power of x. And we're interested in polynomials, symmetric polynomial functions of the eigenvalues. And the eigenvalues are only supported with eigenangles between 0 and pi, so they certainly have bounded support. So this applies to all the random variables that we're interested in. So for all the random variables we want to look at, like say a1 or a2, they have a sequence of moments defined for every n. But a slightly more subtle question is, and maybe to motivate why we should be interested in looking at the moment sequences, is when does the sequence of moments determine the probability density function of x? So there's a standard condition for that, known as Kalman's condition. This is a sufficient condition. They're actually slightly weaker necessary conditions, but this will be good enough for our purposes. And so Kalman's condition says that if you compute the sum from going from n is 1 to infinity of the 2nth moment of x raised to the negative 1 over 2n power. So this is counterintuitive. So the moment's going down on the bottom. So this is, we want this, what we want is the moments to not grow too quickly. And Kalman's condition says that we want this sequence to be unbounded, to be infinite. And that's another way of saying that since these moments are in the denominator, that they're not growing too quickly. So let's check that the random variables we're interested in satisfy this. So we know from the Weyl bounds that for in any fixed genus G, if we take any of our coefficients of our L polynomial, actually forget about what I said about the Weyl bounds, I'm just talking about USP2G. So the eigenangles, these are symmetric functions of eigenvalues that are on the unit circle. So they're bounded by 2 to the G, certainly. So this implies that if I take the 2nth moment, 1 over the 2nth moment, that's certainly going to be greater than 1 over 2, because I'm taking an even moment. It's going to be positive. And it's going to be greater than 1 over 2 to the 2gn. And then if I consider Kalman's condition, I want to check that. If I take the 2nth moment of a1 raised to the minus 1 over 2n, well, that's going to be greater than 2g. So certainly this infinite sum is going to be unbounded for all of our coefficients a sub I, rather. Okay. So what does this tell us? It tells us that if we know the moment sequence of any of our AIs or any symmetric function of the eigenangles, we know its distribution. Okay. it is worth remembering that knowing the moment sequences of A1 and A2 does not uniquely determine the joint distribution. So there might be situations where that didn't give us enough information. In genus 2, it turns out all the distributions we're interested in are uniquely determined by the separate the moment sequences of A1 and A2. But in general, we might need more. But I'll note that we could consider other random variables that would be easy to compute, like maybe A1 times A2, for example. So you could certainly you would certainly expect that in any genus you could cook up some combination of functions that would be easy to compute just from the L polynomials that would allow you uniquely to determine the distributions of all the Sato-Tate groups. Okay. Yeah, and I guess the one other fact I'll mention that is just useful to remember is if we have two independent random variables, and we know their moment sequences, it's easy to compute the moment sequence of their sum. So the nth moment of the sum of x and y is, of course, just the expected value of x plus y to the n, and applying the binomial theorem, sum k equals 0 to n, and choose k. And now applying independence, so I can obviously linearity of expectation, I can take out the sum. If the random variables are independent, I can also distribute it over the products, and I can rewrite this as sum k equals 0 to n, and choose k. Take the kth moment of x times the n minus kth moment of y. Okay, so this is just a binomial convolution. If you're used to thinking in terms of moment-generating functions, a moment-generating function is the exponential generating function of the moment sequence. This corresponds to just taking the product of the moment-generating functions. But I'll just keep things in terms of moment sequences since it's a little more concrete for what we're doing. So now let's compute the moments in genus 1. Again, we've already seen these, but just as a check of what we're doing. So there are three Sato-Tate groups that can show up in genus 1. The generic case is SU2. Which, remember, is the same as USP2. And so just using our probability density function for A1, or in terms, actually it'll be easier to write in terms of the eigenvalues, eigenangles. So we want, so the A1 is minus 2 cosine theta. We want to take the nth power of that because we're trying to compute the expectation of the nth power of our random variable. And then we apply the Sato-Tate measure. And if you just integrate by parts, it's not hard to figure out that this is 0 whenever n is odd. You can see that just from the symmetry. And otherwise, it's a Catalan number. So this is, which I could write as so this is 1 over n over 2 plus 1 times n, choose n over 2. I'm just going to denote this because we're going to use this sequence over and over. I'll just denote this as C sub n, defined for both n even and odd. It's 0 whenever n is odd. And so this sequence looks like 1, 0, 1, 0, 2, 0, 5, 0, 14, dot, dot, dot. Okay. So the Catalan numbers with zeros interleaved. Okay, then the U1 case. Well, I didn't tell you what the density function was on U1, but that's pretty easy to figure out. The only question is what's the normalization? It's 1 over pi d theta in terms of the eigenangle. And so if I compute the moment of A1 for U1, it's 1 over pi, interval from 0 to pi, 2 cosine theta to the n d theta. And this is just either 0 or n choose n over 2. So this again for n odd and n even. And I'll denote these moments by b sub n. So C sub n here, C is for Catalan, B is for central binomial coefficient. And these are 1, 0, 2, 0, 6. And then the third case, and this is what we get if we have a CM elliptic curve over Q, we're always going to be in this situation. We're going to get the normalizer of U1. And what does the normalizer of U1 look like? Well, I'm thinking of U1 now as embedded in SU2, of course. So we could take this as the group generated by, so here's our U1. We could write these as e to the I theta, 0, e to the minus I theta. And then I could throw in the matrix 0, 1, negative 1, 0. So this is the normalizer of U1 as it's embedded in SU2. It has two components. It has a U1, and on the other coset, this has the property of switching these off the diagonal, so the trace is always 0. So I can compute the moments here just by summing over the two components, right? From the translation invariance of the Haar measure, once we know how to compute things on the identity component, it's easy enough to figure out what to do in all the other components, and then we just take an average. We average over the components. I mean, maybe a trivial thing I didn't mention, I guess I've erased it now. The Haar measure on a finite group is always the uniform distribution. If you have, okay. All right, so this is just going to be 1/2, because we have two components, so we're averaging over the number of components. On one of them, we always get 0, so I'll write this as 0 to the n. Again, conveniently remember that 0 to 0 is 1, plus n choose n over 2. And this looks like 1, 0, 1, 0, 3, 0, 10. So these are exactly the moments we saw for a CM elliptic curve over Q. Okay, so these are our three cases. All right, so now we want to look at genus 2. Okay, and I guess I'll move. Is this piano in the way over here? No? Okay. All right. So genus 2, recall there were 6 possibilities for the identity component of a Sato-Tate group, and I'm going to run through them from the highest dimension to lowest dimension. So the generic case is USP4. I'm not going to work out the detail, so it's straightforward but somewhat involved to work this out. I'll refer you to, I think it's reference 9 in the notes. These are worked out in glorious detail, and we have there's a very nice formula you can write down as a determinantal formula in terms of moment generating functions that will give the moments of the kth symmetric power, or kth power sums of the eigenvalues that works for all genus. But when you plug in the numbers for genus 2, you find that the moments for A1 look like Cn. So Cn here is the same Cn here. Cn times Cn plus 4 minus Cn plus 2 squared. Now, if n is odd, all three of these indices are odd, and so I'm going to get zeros here. But when n is even, I'm going to get something else. And if you plug in the numbers, you find that this turns out to be and as I mentioned on Monday, the sequence actually corresponds to counting random walks in the Weyl chamber for USP4, or you can think of this as an analog of the Catalan numbers. We're counting walks that return to the origin and stay within this region. Walks on a two-dimensional integer lattice. Okay. And the formula for A2 is a little more complicated. It actually turns out to be simpler to compute it, the moment sequence for A2 minus 2 first. And this one has a nice formula. That also can be written in terms of these CNs. So here, if n is even, this is going to be non-zero, but this will be 0. And if n is odd, this is going to be 0, and this is going to be non-zero. So these moments are going to go positive and negative, alternating. And they turn out to be, so if I plug in the numbers here, I'm going to get 1, minus 1, 2, minus 4, 10, minus 25, 70, etc. Now, what I'm actually interested in are the moments of A2. Okay, but now I'm going to realize that A2 is this random variable plus 2. And this random variable and 2 are independent random variables. So I can compute the moments of A2 by taking the binomial convolution of the random variable 2 with this moment sequence. So to do that, I'll just write down the moment sequence for the random variable 2, just the powers of 2, of course. And now I'm going to compute the binomial convolution. So I start with taking this times this. That's 1. I'm always going to get a 1 there. Then for the next one, I take 2 times 1 plus minus 1 times 1. And I'm multiplying by 2 choose 0 and 2 choose, 2 choose 0 and 2 choose 2. Sorry. 1 choose 0 and 1 choose 1. And I'm going to get 1 here. 2 minus 1 is 1. And then here I'm going to take 4 times 1 plus 2. That's 6. Minus 1 times 2 choose 1. So minus 4. 6 minus 4 is 2. And if I keep going here, okay. And this is why it's convenient to have these 0th moments here, because when you want to just sit down and crank out these binomial convolutions, it's very important that you remember this. You need this digit here in your sequence. Okay. I mentioned this because this is going to be relevant for computing all the other sequences and also the sequences that are related to the tutorial that you were assigned looking at the curves, the genus 3 hyperelliptic curves. Okay, I'll get to that in a little bit. So this is the generic case. Now let's do some of the easier cases. So SU2 cross SU2. Well, let's think about this. We're going to embed SU2, 2 copies of SU2 in USP4. We may as well embed it diagonally. So we'll have an SU2 up here and an SU2 down here. And this is a product of 2 elliptic curves without CM that are not isogynous. So there's no correlation between them. They're independent random variables. And so in order to compute the moment sequence of the A1 coefficient minus the trace, it's enough for me to just consider the sum of 2 random variables that are the moment sequences for the trace on 2 different copies of SU2 that are independent. So what does that mean? It means I want to take the convolution of my CNs, two of them, and so I get 1. So now these are all going to stay 0. 1 times 1 plus 1 times 1 is going to be 2, 0. Here I'm going to get 2 plus 1 times 4 choose 2 is 6, makes 10, and so on. So I get 70. Okay. And similarly, to compute SU2 cross U1, I do the exact same thing, except now I want to put down the moment sequence, take the convolution with the moment sequence for U1. And when I crank out the convolution, I get 1, 0, 3, 0, 20, 0, 175. And similarly, we can do U1 cross U1. And here, interesting combinatorial identity, these are all just going to be squares. Okay, exercise to prove that. All right, but there are 2 others. So we could also get the Sato-Tate group corresponding to an abelian surface that is isogynous to the square of an elliptic curve. Okay, so now I have 2 copies of SU2, but they're not independent. They're the same SU2. I'm going to see the same submatrix up here and the same submatrix up down here. So when I take the trace, I'm just going to be doubling the trace of an elliptic curve without CM. And so I want to compute the moments of that. Well, that's easy. That's just going to be 2, I'm going to take 2 times the A1 random variable raised to the nth power, but I can just pull out the 2 to the n. And I know what the moment sequence is for SU2 is just Cn. So I'm going to get 2n Cn. And similarly for U1, I'm going to have, this is an abelian surface that's isogynous to the square of a CM curve. And this is going to be just 2 to the n times Bn. Okay. So these look like 1, 0, 4, 0, 32, 320, And these are 1, 0, 8. Okay, so exercise. In genus 3, and I'm going to put a little subscript 2 on here to indicate that I have 2 copies of SU2 that are the same. In genus 3, compute the moment sequence of 3 copies of U1. This would be an abelian threefold that's isogenous to the cube of an elliptic curve with Cm. Hint, one of the 2 examples that you were given has this Sato-Tate has this as its identity component. You're not going to see this sequence over Q. You're going to have to go to a suitable extension field to see it. And the other one, I'm not going to tell you which one's which, looks like this. So it's isogenous to the product of an abelian surface that is isogenous to the square of an elliptic curve with Cm and a Cm elliptic curve. Okay. And so using the techniques that I've shown you, you know how to do products, take convolutions, and when you just have copies, you just put in an appropriate power here. Question? That's okay. Yeah. Correct. Yeah, so this, in order to get all the way down to the identity component, I'm going to have to, this is going to have to be over a field where the Cm is defined. Then I would use the other sequence, yeah. And you'd find out with a little calculation that SU2 cross the normalizer of U1 is actually the normalizer of SU2 cross U1. Good question. Any other question? Yeah. Correct. So that's why we had a 2n c to the n here. What I'm saying here is that the trace is just double the trace of whatever the elliptic curve is. Okay, does that make sense? Yeah. Now, I need to be careful here when I say isogenous. Here this means where the isogeny is defined over the base field. Okay, things get more interesting when the isogeny is only defined over an extension field, because then looking over my field of definition, there could be twisting going on. Okay, and so then things get more complicated. I'm going to show some examples of that in a moment, but I wanted to deal with the identity cases first. So these identity components, these connected groups, this is what you're going to see when you're working over a field over which all the endomorphisms of the abelian variety are defined. Okay, so once if you take your abelian variety, as you change, think of you can recall that the component group of the Sato-Tate group is isomorphic to the Galois group of the field over which all the endomorphisms are defined. That was our big K, and the field of definition of the abelian variety. That was our little k. Okay, and from the Galois correspondence, as we move up within that tower of fields between little k and big K, we're going to be shrinking the component group of the Sato-Tate group. We're not going to change the identity component, but we're going to make the component group of the Sato-Tate group smaller. And if we get all the way up to big K, and that includes any field that contains big K, if we go too far, that's okay, we're always going to see the identity component. Yep. Sorry? That's all we'll see, is just the identity component. So we'll see the Sato-Tate distribution for the identity component. So one of the games that you play when you're trying to figure out, somebody gives you an abelian variety, just looking at the coefficients, say, give you a genus 3 hyperelliptic curve, like the examples I gave you. Well, those have some structure. You might, if you're clever and know a bit of arithmetic, you might be able to figure out what the Sato-Tate group is from first principles. But in general, if I just write down a hyperelliptic curve or give you a description of an abelian variety, it's going to be very hard staring at the coefficients of the curve to figure out what is the field over which all the endomorphisms are defined. But if I go and compute the Sato-Tate statistics, the moment statistics, say of A1, and I could also look at A2, A3, etc., then I could compare them to my list that I've computed. I know in genus 2, I know all of the possible identity components. It turns out in genus 3 there are 15 possibilities, but the only 2 that you have to worry about for the exercise are these 2. So that's why I'm giving you that as a hint. if you compute these moment sequences and then you take the curves that I gave you, I'm telling you that if you go up over a big enough number field, you're going to see one of these two sequences for each of them. Okay, and then it's sort of a game, and I'll spend some more time on this. I don't want to spoil the fun, but tomorrow afternoon I'll spend some time on going through some of those examples for these specific curves. But the nice thing is you don't have to guess big K exactly. You just need to get anything that contains big K. So you can start by throwing in some obvious things, like if we know there's CM elliptic curves involved, the good guess would be to throw in fields over which CM is likely to be defined. And I'll give you a hint there. The J invariant 0 and 17, 28 curves have a habit of showing up a lot. So Q, looking over Q adjoined I or Q adjoined square root of minus 3, those would be good things, good fields to start with. You're going to need a little bit more than that. But if you go up over, I mean, remember, in Genus 2, the largest component group we saw had 48 components. So that means the big K has degree 48 over Q. So you may need to go to a much bigger one. These examples, you don't need to go quite that high. Yeah. Any other questions before I move on to giving an example with non-trivial component group? Yeah. Yeah, thanks. Mm-hmm. Ah, yes. Yeah, so this is... Yeah, so maybe Francesca can say more about that. But that's quite important. I've been talking about the endomorphism algebras, but there's not a one-to-one correspondence between. This is why we really need to talk about Galois types. But if you're just looking at if we just talk about endomorphism rings, there's not a one-to-one correspondence between Sato-Tate groups and endomorphism ring. You can get very different curves with very different endomorphism rings, including a simple and a split Jacobians. Abelian surfaces that have the same Sato-Tate group, okay, and the converse can happen too. You can get different Sato-Tate groups for curves whose endomorphism algebras are the same, different component groups. Okay. Yeah, I wouldn't say anything. I'll let Frances deal with that one. So I need one more blackboard, I guess. Is there? So I wanted to just do one example of a group whose component group isn't trivial, just so you can see how that's done. It's generally quite straightforward. So I'm going to take most of these in Genus 2 show up with identity component U1. So let's take that example. So just explicitly, we're going to embed our U1 in USP4. There's a lot of different choices. Conjugate choices aren't going to make any difference, but just to be concrete, I'll write one down. Yeah, we'll do this one. So here U is something on the unit circle, an element of our U1. Okay, so I'm sending this U to this matrix in USP4. And now let's define Z sub k to be this matrix whose diagonal elements are 2 kth roots of unity. And now why did I take 2 kth roots of unity? Well, the thing to keep in mind is that if I take, is that both plus and minus the identity are in U1, in my copy of U1 embedded in USP4, which means that if I take my matrix C to the k and raise it to the kth power, I'm going to get -1, and that's in my embedded U1. So if I consider the group, which I'll denote for obvious reasons, CK, generated by my embedded U1, and this matrix ZK, its component group, so its identity component is going to be U1, but its component group, so if I take the quotient, so CK0, by that I mean the identity component, is going to be cyclic of order K. Okay, and if I wanted to specifically identify the elements of this, I could just take, explicitly, this is just going to be ZK to 0 times u1 zk to 1 times u1. Okay, so these are the components. And we want to compute the moments of the trace on each of these components, and then averaging those moments over the components will give us the moment distribution of the group. Okay, but the first question we should think about is which k's are possible. I mean, there are infinitely many of these groups. Not all of them show up as Sato-Tate groups. So which ones do? Well, we'll recall the rationality axiom. I think it was ST3. Which says that if we integrate over any character, we need to get an integer. I'm going to pick a particular one. So if I take, I'm going to denote this matrix here with a capital U. Okay. So capital U over my U1, which is embedded in USP4, of course. If I integrate the trace of the matrix ZKU, and I'm going to take the square of the trace. I can take any character I want. I'll take that one. Against the Haar measure for this group. And because it's translation invariant, I know it's the same as the Haar measure for our U1, again embedded in USP4. This has to be an integer. Okay. Well, when does that happen? Well, that's going to happen if and only if when I take the sum of the 2kth root of unity and its conjugate and square it, I better get an integer. And this is going to happen if and only if k is 1, 2, 3, 4, or 6. So this tells us that there are 5, obviously this is just the trivial case, so there's 4 non-trivial cyclic groups of this form. These aren't the only cyclic groups. There are other Sato-Tate groups that are have component groups that are isomorphic, but they're embedded differently and they have different trace A1 and A2 distributions. I'm just considering one particular example that's the simplest case. Question? Yeah. Yes, embedded as you see here. Yep. Yeah, you're right. I've written this wrong. You're right. Yeah. Thank you. Yeah. Mm-hmm. Yeah, I should put. Yep. Any other question? Yeah, I mean, there is a subtle issue here. That it's very important to be explicit about these embeddings. It's not a huge. I mean, even in Genus 2, it already causes complications. In Genus 3, I mentioned that there were 15 possibilities for the identity component. As abstractly groups, there's actually only 14. The 15 come from the fact that there's 2 different ways of embedding a particular real Lie algebra in USP6, and they give different Sato-Tate distributions. So it's not enough it's not just an exercise in considering these groups abstractly. It matters how you embed them in the USP2G that you're working in. Okay. But this is maybe the simplest example of how we can constrain the possible Sato-Tate groups of this form, and now we can compute the moments. So let's do that. How am I doing? Yeah, 5 minutes, almost done. So for the Sato-Tate group CK, I'll just do the A1 moments. So for A1, well, I'm going to sum over the components, which I've written down here. So I'm going to take j going from 0 to k minus 1. I'm going to need to divide by 1 over k. And I'm going to have zeta 2kth root of unity raised to the jth power plus its conjugate. And then I'm going to end up multiplying by b sub n. This corresponds to the moment for the u1. Okay. And when I work this out, so in the trivial case, I'm going to get 2n b then. We've already seen this. This is exactly this one here. Okay. So that's the identity component of my embedded u1. So this is k equals 1. In the second case, I'm going to get 1/2. So now I have a 4th root of unity. So I start with the identity. So that's going to give me 2 to the n. And now when I take the first power of my 4th root of unity, I have I and minus I. And the trace is 0. So I get a 0, but I'm going to make sure I always remember to write it as 0 to the n, because 0 to the 0 is not 0. And I'm going to put a bn. And then similarly for k equals 3, I'm going to get a 2 to the n. So now I have a 6th root of unity, and I add it to its conjugate. I'm going to get 1 to the n. And then when I take a 3rd root of unity and add its conjugate, I'm going to get negative 1 to the n. Of course, these are only non-zero. This bn is non-zero only when n is even, so I could treat that as a 1 to the n if I like. And for now I consider 8th roots of unity. I'm going to get a square root of 2 raised to the nth power, which I'll write as 2 to the n over 2. So 0 to the n. Now I have a minus square root of 2 raised to the nth power, which is also 2 to the n over 2. So this k equals 4. And then lastly, for the 6th root of unity, I'm going to get a 2 to the n plus 3 to the n over 2, plus a 1 to the n, plus 0 to the n, plus minus 1 to the n, plus 3 to the n over 2 times bn. This is for k equals 6. Okay, so there's these 5 possibilities. And the last thing I want to mention is just to give none of these actually show up over Q. So I wanted to give you one that does. So I'm going to define J of CK. You might remember this notation from the table I showed you. So this is what we get when we take the group generated by our embedded U1, our ZK, and the matrix J, where J here is this matrix, 0, 0, 1, minus 1, 0, 0, minus 1, 1, 0. Okay. This is actually happens to be the symplectic form that we use on USP4. But we can throw it in there. And so now what happens when we multiply, so now we've got 2k components instead of just k components. And any of the cosets that involving j, if we apply, so this is just the same as taking j times each of the components of ck, they're going to have trace 0. This is going to move the diagonal elements off diagonal. And so it's very easy to compute the moments. So mn, so let's just do, say for k equals 6. So j of c 6. So this is going to be a component group of order 12. It's actually the dihedral group of order 12. And its moments are going to look like, so now I'm going to have a 1/12. And I'm going to have, so for the non-zero components where I have non-zero traces are going to be exactly the same. I just repeat those. I'm just collecting terms here. 2 times 3. I have 2 3 to the n over 2s. I have 2 1 to the n's, which I could just write as 2. But now I have, in addition, I had one component out of the 6 where I had trace 0. Now I have 6 more components where I have trace 0. So I want to put a 7 times 0 to the n. Be the n. Now, of course, that does nothing except when n is 0, it makes the moment 1. But it's actually quite useful to know this, because what it tells you is that if, and this is going to be also useful to you if you're experimenting with the 2 hyperelliptic curve example, genus 3 hyperelliptic curves I gave you as an example. If I look at if I compute the moments for this group, I'm going to see a spike in the middle. And I can compute, because there's 7 out of 12 components that have trace 0. And I can count how often do I get trace 0. And if I compute the proportion of time that I get trace 0, that's going to be a useful number to me. It's going to be 7/12. And if I compute that to high precision, and I know it's got to be a rational number, and I know the denominator can't be that big. In genus 2, I know that it can't be more than 48, and in genus 3, what is the bound? 216 something. Anyway, it's a reasonably small, smooth number. So if you compute for each of the examples I gave you, it will be useful for you to not only compute the moments, but try to see if you can figure out how many components of the Sato-Tate group, or at least the proportion of components that have trace 0. So if I were to just write down, a genus 2 curve with this Sato-Tate group, I guarantee you that the coefficients are quite complicated. It'd be very hard for you to tell from looking at the coefficients that there was anything weird about this curve per se. But if you were to compute it, start computing A1 values at reductions mod p, you'd quickly notice, you wouldn't have to go that far before you'd notice that it looked like about 7/12 of the traces were 0. And that would immediately tell you that 12 better divide the order of the component group of the Sato-Tate group. It also gives you a hint if you're trying to figure out what big K is, as you extend your field of definition of the abelian variety you're working with. If you're seeing a spike at 0 in the A1 distribution, you know you haven't gotten big K yet. Okay. All right, I think I'll stop there.